Since it's our first video, let's look at some very simple implicit derivatives, which means we need an implicit equation. And here we have a very nice basic implicit equation. The reason this is an implicit equation is because solving for y is not fruitful. You can't get y equals. When you take the square root, you would actually have a plus or minus in two pieces. So really, this is an equation. This is not an explicit equation. It's an implicit equation. So how does one take the derivative of this? Well, first you need to know which derivative you're looking for. So let's just say in this example, I'm looking for dx dy. So that's very important to me. Notice it's not the typical dy dx. I'm looking for dx dy. How do I do it? Well, what I'm going to do is I'm going to take the derivative of both sides, the derivative of the left-hand side and the derivative of the right-hand side. I'm actually going to use all the rules we know. There is no new rules. The derivative of 4x squared should be like you think it is. It is 8x. But here's the rub. Right now, because it's dx, the derivative of the x function with respect to the y variable, because x stands for a function now, we really don't know what's going on inside of x. This could be a very complicated function. We just called it the letter x. Because of that, we're going to do a times x prime. And that's because we don't know. We take the derivative of this using the good old power rule, but by the chain rule, we have to take the derivative of the inside, which is x prime, which we don't know. And honestly, we don't really need to know. Plus, because when you take a derivative at a plus, you can split it into one piece, take its derivative, find the next piece, and take its derivative. So the derivative of y squared, well, that is a good old 2y. And in this case, I don't need anything extra because it's the bottom variable. It's the derivative with respect to. So y squared, the derivative is 2y. All right, we took the derivative of the left-hand side. Now let's take the derivative of the right-hand side. The derivative of 16x should be 16. It is. But again, we have that x. What I look for is the numerator. If I have the numerator variable, which is ex, I will know after I take the derivative, I'm going to have to attach by multiplication that x prime. The reason for is, again, I've assigned x a function, a deeper, more meaningful function that I don't know about. So that's how you take the derivative. I still want dx dy. Well, guess what? A shorthand symbol for dx dy is x prime. All right, dx dy, the shorthand symbol is x prime. So now this becomes a algebra question. I want to solve for just get x prime by itself. To do that, I have an x prime on this side and an x prime on this side. Not good. I'm going to do what it takes to get the x primes to the left-hand side. What that means is I'm going to subtract the 16x prime over. But that 2y that's in green, I want to move it to the right-hand side because that 2y does not have an x prime multiplied by it. That's really what I'm looking for. If I have an expression multiplied by x prime, move it to the left. If it doesn't, move it to the right. I see three terms. 1, 2, 3 terms. I move 2 to the left and left 1 on the right. Now, everything on the left has an x prime. Because we have good algebra skills, you should know what I'm about to do next, and that is factor an x prime out. If you factor an x prime out, you're left with 8x minus 16. And that makes sense because if I distribute x prime back through, 8x times x prime is 8x prime times 16 is 16x prime. So I know how to factor because I know how to distribute. Awesome. And this is honestly the same 3 steps I do in the algebra component. See, again, I took the derivative here. The derivative rules are done. Now it's algebra time. Move everything with the x prime to the left. First step. Everything else to the right. Factor out the x prime, because everything should have an x prime. Last but not least, to get x prime, what I'm looking for, which is dx dy, x prime and dx dy are the same notation. My answer will be, I have a negative 2y on the right-hand side. I'm going to divide over this parentheses. Why? Well, it's x prime times, right there. That's a times. It's x prime times this expression. To get rid of a times, you would divide it over. And so that's why my answer, my final answer, is x prime equals negative 2y divided by 8x minus 16. You notice my answer is a little bit more complicated than usual, but that happens when you're dealing with implicit expressions or implicit equations. We are done. Now I'm just looking for somebody to give me numbers x and y to plug in. If I want the actual value for x prime, that is the derivative of x with respect to y, this rate of change, I would need to now know what x and y are. If x is 3 and y is 4, I'd plug in and get me a number and tell you what that means. In later videos, you will see that. Hello, everybody. So, on to our next example. Another, slightly more difficult, but along the same path. Let's say we have 4 natural log of y plus 6x, let's go a little thick here, 6x equals 10x cubed. Now, we still got to decide. Here's our equation. It's an implicit equation because solving for y could find very difficult. I still want to find the derivative. Which derivative is going to be very important here? Is it dy dx? Is it dx dy? Or is it some type of dx dt? How do you know which one it is? You'll have to read the question. So for example, let's say we want dy dx. So how would I take this derivative? Well, just like before, we go with the derivative of the left-hand side, derivative of the right-hand side. Please note y now is the top letter, which means x is with respect to x is a nice letter. What do I mean by that? Well, let's take the derivative and find out. Well, the derivative of the natural log is pretty simple when there's a constant. The derivative of the natural log is, the derivative of the natural log is 1 over the inside times the derivative of the inside. Remember the rule for the derivative of the natural log. The derivative of the natural log is 1 over the inside of the log times the derivative of the inside. The derivative of y, well, now y is the numerator. The derivative of y should be 1, but because it's the numerator variable in my expression, I got to write y prime. And I want to make sure that's very clear that that's y prime there. So that's y prime. Plus the derivative of 6x, well, that's 6. That's nice and simple. And no, I don't need anything extra because that's the bottom letter. That's the letter that is the variable that is with respect to. So the derivative of 6x is good old 6. That equals, all right, the derivative of 10x cubed is 30x squared. If you notice, I'm just doing the rules like I've learned. And then I pause for a moment to go over to check, all right, is with respect to x. So this is good, it's straight to the point, nothing needed. If I take the derivative with respect to the top variable, the y, the function, I do have to do the chain rule. So after I take the derivative, I have to multiply by the y prime, for I do not know what the y stands for. So there is my derivative. From here, it's again algebra time. First rule of algebra. If it has a y prime, keep it on the left. If it doesn't, and here's a piece, and here's a piece, so we have 3 terms, all right? 1, 2, 3 terms. This term is the only term that has a y prime. I will keep it here. This term does not have a y prime. To get rid of a plus, I will subtract it over. So I have 4, whoopsie, I have 4 over y, because that's what happens when you multiply 4 times 1 over y, times y prime equals 30x squared minus 6. Again, I subtracted the 6 over. Next step of algebra. Everything on the left better have a y prime. It does. All right, I factor it out. You don't need to factor. There's only one term over here, but I would factor it out. There was 4 terms, like the preceding example. All right, this is the multiplier of the y prime. I'm going to divide that over and be done with this question. Y prime will be 30x squared minus 6 all over the expression 4 over y. And once again, I wait for an x and y to plug in. You give me the x, you give me the y, and I'll give you your y prime. Now, y prime is like we typically know. That is the slope. So I'm looking for the slope. In terms of rate of change, remember, y prime is also the, the derivative of y with respect to the variable x. I'm having a very hard time writing the d there. There. So y prime stands for dy dx, the derivative of y with respect to x. And so really, if we plug in x and y, we're really looking for, as I increase x by 1 unit, what happens to the y? That's really what we're looking for. When I plug in the point, whatever the point is for x and y that I'm allowed to plug in, I'm really looking for, as x increases by 1 unit, what happens to this y? That's the typical definition of slope. Thank you for watching this video.